Welcome to Study Loop.
This is problem 99 in chapter 7.4 of Vector Mechanics for Engineers, Statics, and Dynamics. So in this problem, a cable stretches from A to E, and there are 3 loads applied, one at B, which is 2 kips, one at C, 2 kips, and one at D, also 2 kips. The vertical distance from A to E is 7.5 feet. The horizontal distance from A to B is 6 feet. From B to C is 9 feet. C to D is 6 feet. And D to E is 9 feet. And the vertical distance from C to E is 15 feet. And for A, we have to find the vertical distance from B to E, the distance B, and the vertical distance from D to E, which is the distance D. And also for part B, we had to find the max tension in this cable. All right, so the first thing we're going to do is draw a free body diagram of the whole entire cable from A to E. And we're going to start off with taking the moment of A and set that equal to 0. This will be EY times 30 because there is 30 feet in the horizontal direction between A and E. We're going to subtract EX times 7.5 because there are 7.5 feet in the vertical direction between A and E. And we're going to subtract 2 times 21 for the load at D. And there's 20, and there it's times 21 because there's 21 feet between A and D in the horizontal direction, minus 2, which is the load at C, times 15 because there's 15 feet in the horizontal direction between A and C, minus 2 times 6, and this is the load at B. And there is 6 feet between A and B in the horizontal direction. So we're going to simplify this. So this is 30 EY minus 7.5 EX. And we're going to move all the loads to the other side, and it totals 84. All right, we're going to go ahead and start isolating EX. So we're going to move EY to the other side. Like so. And we're going to go ahead and solve for EX. It's not going to be simplified, but it's how we're going to start solving it. And because it's negative 30 over negative 7.5, this will become positive. All right, so in the next step, we're going to actually have to use this later. So we're going to do that. All right, so for the next step, we're going to do a free body diagram from C to E. And we're going to do the sum of moments around C and set that equal to 0. We're going to do EY times 15 because there's 15 feet in the horizontal direction between C and E. We're going to subtract EX times 15 as well because there is 15 feet in the vertical direction between C and E. And we're subtract 2 times 6, which is the load at D. It creates a negative moment around C because it's in the clockwise direction, and it's times 6 because there's 6 feet in between C and D in the horizontal direction, and it equals 0. So we're going to go ahead and simplify. So 15 EY minus 15 EX. We're going to go ahead and move the 2 times 6 over to the other side, so it's going to be positive 12. So we can go back to what we just found. We're going to plug in the EX into this equation so we can solve. So negative 15, oops, negative 15 EY minus 15 EX, which is negative 84 over 7.5. plus 30 over 7.5 EY, right, equals 12. So we're going to go ahead and distribute that 15 into this equation, and it's going to simplify. So 15 EY plus 168 minus 60 EY equals 12. So let's go ahead and solve for EY. So EY will equal 3.467 kips. All right, and we can go ahead and plug this into the EX equation again, which was negative 84 over 7.5 plus 30 over 7.5 EY. We can plug in that value for EY for a total of 2.667 kips. And while we're at it, let's go ahead and solve for the maximum tension, which is this equation. The maximum tension equals T equals the square root of EX squared plus EY squared. And plugging in those values, we get 4.374 kips. And this is actually the answer for part B. Okay. But going back to part A now, we're going to use the free body diagram from D to E. And we're going to take the sum of moments around D and set that equal to 0. And it's going to equal positive EY times 9 because there's 9 feet in the horizontal direction between D and E, minus EX times DD, the distance of D. So simplifying, this will be 3.467 times 9 minus EX, which is 2.667 times DD, so that equal to 0. All right, go ahead and solve for the distance of D, which equals 11.7 feet. That's one of the answers for part A. And now we're going to take into account the whole cable, which I didn't draw it again, but we're going to take into account the whole cable and do the sum of forces in the y direction so that equal to 0. So it's going to equal positive AY because it's in the positive y direction, minus all the loads, and then plus EY, which is also in the positive y direction. So simplifying, and EY was 3.467, go to 0. So I'm going to solve for AY, which equals 2.533 kips. And then we're going to go ahead and do the sum of forces in the x direction as well. Set that equal to 0. And this equals negative AX because we put the AX in the negative x direction, plus EX. So this is negative AX plus 2.667 equals 0. So AX equals 2.667 kips. All right, so we can go ahead and solve for DB now. We're going to take a free body diagram from A to B, do the sum, moments around B, and set that equal to 0. It will be AX times the distance of B minus 7.5 minus AY times 6 because there is 6 feet between A and B in the horizontal direction. So simplifying, is 2.667 times the distance of B minus 7.5 minus 2.533 times 6 equals 0. So you can go ahead and solve all of this and simplify down to dB equals 13.2 feet, which is the rest of the answer for part A. So the distance of D equals 11.7 feet, and the distance of B is 13.2 feet. These are the answers for A. And solved previously using the reaction forces at E, we solved for the maximum tension, which is 4.374 kips, and that is the answer for B. And this is for problem 99.